Okay. Thanks for the introduction. Good morning, everyone. Thank you for being here. My name is Dejing. As the title says, this talk is about a new algorithm for real-time rendering of stereo-consistent contours. So first, I'll talk about the motivation of our work. Contour rendering is a concise method to depict the shape of an object. This is a figure of contours that render from a bounding model. With the rapid development of VR, the extension of the contour rendering to stereo rendering arises as an interesting topic. This figure is an example of stereo rendering of contours. The blue lines are contours observed from the left eye, and red lines are contours observed from the right eye. Obviously, contours in 3D will provide more information of the shape of the object. However, stereo rendering of contours may induce binocular rivalry, which will cause viewing discomfort. In this figure, you can notice that some contour segments that are visible at one view, but they do not have visible counterpart in the other view. These inconsistent parts of contours are highlighted by yellow circles. To avoid binocular rivalry, we must render stereo-consistent contours. Researchers have already made some efforts in this field. In 2013, King and his colleagues firstly addressed this problem and presented a method. They introduced the concept of epipolar-slidability and successfully achieved the stereo-consistent rendering of contours. Specifically, they introduced a criteria named as epipolar-slidability to detect the consistency of contours at stereo views. I will use this top view figure to explain this concept. In this figure, the letter L and R denote the left and right eyes, and whereas the PL and PR are the corresponding contour points. With the while the viewpoint E moves from L to R, the corresponding contour point X should move from PL to PR along a curve called the epipolar curve. If the contour point on the epipolar curve continues from PL to PR, we say that PL is epipolar-slidable. Otherwise, if the contour point on the epipolar curve does not continue from PL to PR, PL is not epipolar-slidable. To test the epipolar-slidability in their method, they render images at multiple viewpoints between two eyes and check the continuity of the contour points among these images. Once contours are not epipolar-slidable, they are erased in the rendering, thus resulting in stereo-consistent contours. As can be seen, their methods needs to render images at multiple viewpoints per frame, which makes it infeasible for real-time applications. In 2018, Buchenberger and his colleagues proposed another method that interpolates contours observed from different viewpoints in object space. This approach heavily relies on the pre-computation and a predefined camera path, which makes it inflexible for real-time application either. In our work, we extend the idea of epipolar-slidable and provide a corollary of it. On the basis of this extension, we design an image space search algorithm to check the epipolar-slidability. Our technique has a much lower cost than those of previous works, therefore enables real-time rendering and editing of stereo-consistent contours. I will explain our corollary we derive for the epipolar-slidability in following slides, but at first, let me introduce some necessary mathematic formulations. The viewpoint E between L and R can be parameterized by a variable T. Based on the definition of contours, we can derive a function of T with we can derive a function of t with respect to the position and normal of the surface point x on the epipolar curve. When x moves along the epipolar curve, the value of p and n change accordingly, so that's the value of t. Therefore, we rewrite them as functions of surface point x. Since the value of t represents the position of E between R and R, we can see Tx as the trajectory function of corresponding viewpoint of the contour point x. By observing the trajectory of corresponding viewpoint, we have a corollary of epipolar-slidability that if PL is epipolar-slidable, the corresponding viewpoint for x moves monotonously from L to R. However, if PL is not epipolar-slidable, the movement of the viewpoint E is not always incremental before it reaches R. In other words, the monotonicity of the trajectory breaks at some extreme points where the derivative of the trajectory function is 0. Based on this observation, the attempt to test the epipolar-slidability can be technically converted to testing the monotonicity of the trajectory of viewpoints. In this way, we can compute and store the extreme point of the trajectory function and realize the epipolar-slidability tags in image space. This is an illustration of our overall algorithm. It mainly includes 3 stages. The first stage is to compute contour points and extreme points. To compute contour points, we find a surface point where the view direction and surface normal are perpendicular. Mathematically, extreme points are points where the value of derivative is 0. But in practice, finding the surface point that satisfies this condition is infeasible because the derivative value is not continuous due to the discrete representation of 3D models. Thus, we compute extreme points by finding the surface points where the sign of the derivative of trajectory function is changed. The second stage is to test epipolar-slidability by an image space search. The image space search process consists of 3 steps. The first step is to reproject the contour points from the current view to another view. The second step is to determine the search direction based on which sign of view range the surface normal points to. If the surface normal points to the right side of view range, we search to the right. Otherwise, we search to the left. The third step is to search in image space pixel by pixel. The search process stops when we reach the pixel having the corresponding contour points of the other view, as shown in the figure on the left, or it stops when we find the monotonicity of the trajectory function phrased at some extreme points, such as PF in the figure on the left. After testing the epipolar-slidability of contour points, the final stage is to render them as contours. Specifically, in this stage, we launch another rendering pass to draw all contours with the design lightweight and remove the contour points that are not epipolar-slidable. The final result is an image of stereo-consistent contours. Here is a comparison of our results and those from previous works. Although they are different in some details, the qualitative comparison reveals that our algorithm achieves a similar stereo consistency. And furthermore, our method has a much lower cost than those of previous works. In King et al.'s works, they achieved 3 frames per second for a scene with 30,000 vertices, and in Brukenberger's et al.'s works, they achieved 24 frames per second for a scene with 20,000 faces. In our work, we achieved 60 frames per second for a scene with 30,000 vertices and 60,000 faces. Therefore, enables the real-time rendering and editing of stereo consistent contours. This is a demo of our work. Since our method is efficient and does not rely on any pre-computation, we can edit the object and train the parameters as designed in real time. In conclusion, we first provide a mathematical extension of epipolar-slidability. Second, we design an image space search algorithm to check epipolar-slidability based on that extension. Third, we propose a real-time rendering technique to draw stereo consistent contours. In the end, I would like to thank our funding agencies for their support and the anonymous reviewers for their valuable comments. Thank you for your attention.
So does anybody have any questions for Dejing here? Yes, please go to the microphone if you can.
I'm just wondering, like, if your result maps well between like a PC GPU system and the systems running on mobile processor, where you would do binning hits, you don't have access to the entire frame, or a lot of constraints come in, right? Do you have any thoughts where your result will be consistent when you go from like a PC-based GPU to a mobile processor?
We implement our pipeline in a PC system, but we have not tried it on a mobile or anything like this. So,
but do you know like what would happen if you don't have access to the entire frame, or like what happens if like the vertices are getting cached differently, they're getting sorted? Would they pose any constraints on your algorithm or not?
I think you have a really great suggestion, but we will think about doing that in future work.
Cool, thank you.
You haven't tried it on the mobile yet, then?
I can answer this question. I think we can do it in the post process. So we do something in the rotary stage and do the post process. So I do not think it will be a problem to transfer this code to a mobile GPU. So I think it's okay.
Great. Would love to chat with you afterwards.
Okay.
Yeah, thank you.
Okay,
Great.
thank you.
Do we have any other questions? I had one question for you. On your results, it was very impressive, the speed up. You know, you were showing, if you go back.
Go back, okay,
slides,
okay.
to the,
Which
this
one?
here.
This one?
Yes.
Oh.
So you were 60 frames per second compared to 3 frames per second, so 20 times faster.
Oh,
That's
yes.
very nice. But this is evaluating just the speed. Do you do anything to evaluate the visual quality or the quality of the solution?
Let's look at this figure. Because we have different implementation to how to draw the contours, and I don't know what the exactly parameter they use to draw these figures. We just tweak the parameter manifoldly to approximate the results. So we cannot actually compare them really precisely. We just visually think that they are at the same level.
Okay, that's good. And have you tried with, you have two objects here, Homer Simpson and kind of Pegasus horse. Have you tried other objects as well?
Yeah, yes, more results are in our paper.
Okay, great. I'll check that one. Good. Okay, let's thank the speaker again.
Thank you.
So now we have Laura.